So today we try and do something, I guess, more fun and do some application. So I want to look at like L functions. Functions, maybe in great generality, just like maybe this is, you can attach such a thing attached to varieties, but more generally to motives. And somehow, so L function, I mean, I will define it and define it as well. Once you define an L function, you can ask some questions. So like, for example, is it meromorphic? An L function is naturally like some kind of series. Series over C. So it's natural to ask whether it's meromorphic. And basically, this is like the content of the Langland's conjecture. So it's related to Langland's conjecture. And also Wiles' proof. Andrew. Wiles' proof of Fermat's last theorem. And I guess next semester I will maybe talk more about this point of view. The point is like, I mean, in the Langland's conjecture, you want to maybe relate, roughly speaking, motives to automorphic representations. And this was also how Wiles proved Fermat's last theorem as well. But essentially, you have some kind of L function here, and you have an L function here. And through this relation, these turn out to be the same. I mean, as a consequence. I mean, you don't know this. This is like a Langland's conjecture, let's say. But the point is, if you can prove some kind of correspondence like this, then you know that the L function attached to automorphic representation, it's naturally meromorphic, usually. So you conclude that this guy is meromorphic as well. But this is not really maybe what we've been discussing in this course. Maybe another type of question you can ask is, where are the zeros located? So like, I mean, one clear example of such a thing is the Riemann hypothesis, right? So Riemann hypothesis predicts that all zeros of the Riemann zeta function are located on the complex real part, a half, I guess. And also, this is also related to the Wiles conjectures. So recall the Wiles conjectures, I mean, you have the L function attached to some variety over a finite field, FQ. And one of the parts of the Wiles conjecture was also so-called Riemann hypothesis, the equivalent, which predicts that the eigenvalues all have some weight, of something, but they are similar kind of things. And I guess like today, you can ask the question is like, so you expect the L function of some motive. I just write it roughly. I mean, I haven't defined it, but it'll be some series. So for example, you should be able to, around s equals t, let's say, it should be some series ai s minus t to the power of I starting from some n, negative maybe. So you can ask for information about, say, first of all, like, you may not be able to evaluate this at t because it could be some pole, but if you can evaluate, so like if n is equal to 0, so the series looks like something like a0 plus a1 s minus t plus a2 s minus t squared plus so on. Like, the natural question is like, what is Lm of t? So, or like a0, what is a0, right? And this is the content of Verligne's conjecture, which I will discuss today. You can also ask, like, in the case like if n is not equal to 0, so in particular if there's some pole or some 0, you can ask like, what is the pole order? Like the pole order is like the value of n, where it starts from. Or you can ask like, what is the leading term? This is the value of an, let's say. So like, I mean, in this case, the L function looks like something like an s minus t to the power of n plus so on. Could be a 0, could be a pole. And this, these two questions here is Berlinson's conjecture. And originally, maybe classically, one like looked at the elliptic curve case when M is basically attached to elliptic curve. Because here M is very general, some motives, it's very complex. But in the elliptic curve case, I mean, it was maybe the Birch-Snitton-Dyer conjecture. So I think that's obviously very famous, right? So it's still unsolved, even for elliptic curve in general. But thanks to maybe, yeah, I don't know. Maybe the baby case, not the baby case, but still difficult clearly. Elliptic curve is BSD, and in general, like in this motivic setup that we discussed today, it's Berlinson's conjecture. So I think Berlinson's conjecture and Verligne's conjecture, wherever I wrote it here, they're basically what I roughly want to discuss today. Does it make sense? But so far we have maybe constructed the derived category of geometric motives, let's say over K, where K is some field. And maybe we basically only studied really effective things, but after inverting the Tate module, or the Tate motive, we get negative twists as well, and this gives the category of geometric motives, not necessarily just effective. And also, this lives like in some category of sheaves, right? Like this, I've been using the notation minus for Nishnevich here, Nishnevich. So this is like some sheaf guy, and these sheaves were valued um, sheaves were valued in a billion groups. So, i.e. Z modules. But you can also imagine that sheaves were valued in some lambda module, where lambda is any ring. So, like this, the story generalizes. So lambda is any ring, maybe nice enough, like commutative, etc., with a 0 and 1. Then you can construct a category of dm minus with k lambda. And typically, we want to look at lambda is rationals. So, yeah, there's this category of maybe Nishtevich sheaves with transfers or geometric motivic complexes, but with sheaves with transferred valued in Q vector spaces. And you can also similarly cut out a corresponding geometric motives with values in Q. I mean, in a certain way you can cut it out. The reason why I'm doing this is because I want to state Berlin-Stein's conjectures and even Deline's conjecture. We need realization functors. So we need to take cohomology of things. And the cohomology usually, the integral case is much more difficult, and it's better to stick with rational coefficients. So it's better to upgrade everything in terms of Q. So at this point, let's just say that I have a category of geometric motives over K with Q coefficients. So you should think of this as sheaves valued in Q vector spaces. And basically, thanks to upgrading from dm gm of k, which basically in our notation here would basically be dm dgm of k of z, right, in a billion groups, to dm gm of k of q, we get realization functors. So I give an example now. We get several realization functors corresponding to different cohomology theories. So I give an example. I mean, this to get the actual realization functors is non-trivial. I mean, so here's an example. Take realization. So there exists a functor. So the setup here is L is some prime, and let's just take characteristic of K to be 0, so I don't have to worry about L not equaling characteristic of K. Then there exists a realization functor, RL, from dm gm of K of Q to the derived category of the Tannakian category of QL bar representations of the absolute Galois group. So you can think of this functor roughly as taking maybe some variety finity x of finite type and mapping it to its tau cohomology. So F maybe has some structure morphism, X maybe has some structure morphism F to K, it lives over K, and I can take a tau cohomology, the tau push forward. Let me write it a bit more clearly. Of QL, maybe bar coefficient, or maybe just QL is enough for our case. Yeah. So it's roughly this functor. Of course, such a functor literally exists, like, I mean, at the level of just varieties, right? Like if I just restrict myself to schemes of finite type to this exists. And the point is, like, you can extend such a functor to the entire category of motives through some formalism, like some that I wrote in words here. But this formalism only works once we upgrade everything to Q. So it's, yeah, I mean, strictly speaking. So it's one reason to upgrade over Q. The other reason, like a tau cohomology, it's a bit easier to consider rational tau cohomology than integral for our story. Okay, so this Tate realization, I'm going to maybe donate this by M gets sent to ML, okay? So some geometric motive, M gets sent to its L-adic Tate realization, which is some object in here. And similarly, I won't spell it out, but there is also Betti realization. Where, let's just for notation, M gets sent to M of B. Given by Betti cohomology. And there's also Duran realization. So here M gets sent to M of D of R, let's say, given by Duran cohomology. I mentioned these realizations in the context of pure motive, like maybe in lecture 5, but maybe in that case it was conjectural because we don't know the standard conjecture. We could not get like the entire, this only covers like rational Chow motives somehow, right? Only rational Chow motives sit in here, but numerical motives don't sit in here. So there was some problem with extending to all the way to numerical in the pure case. But this here is non-conjectural, at least, that part of it. Okay, so let me now write down the definition of the L function. I mean, I can write it down now. So, definition L function. So, given some motive in my, well, some geometric motive, with the sheaves valued in rational vector spaces, then the general definition is the L function attached to M of S is equal to some Euler product of L functions attached to some primes, okay, where this, so I have to also fix maybe some prime L for this, where these factors LP of M of S. So I have this, I have my L-adic realization, which is some Galois representation, and I can take I can take the inertia group invariance, and in that way, I have Frobenius acting on it. And to get a series, I just add like this P minus S here and subtract 1 and take the determinant of this expression. And anyway, maybe minus 1 here. What's important is that I take invariance of the inertia subgroup so that frog P makes sense. Frog P naturally lives in the decomposition group. So conjecturally, so this is also not known, L of P does not depend on S, right? Okay, now we can like try to state Deligne's conjecture. At least for, let's say, for the pure, in the pure case. So in this setting, let's say M is pure. So it essentially comes from the Chow part, right? So M, I guess I use the notation rational motives. K, Q. Or coming from, essentially from some smooth projective variety. In this case, I have we have comparison isomorphisms. So I have the comparison isomorphism I infinity
should we assume L not equal to P?
Yeah.
Okay.
No. Yes, in this case, yes. So maybe I can't fix an L from the beginning. So, yeah. For some prime, L not equal to P. Thanks. So, as I mentioned, like in the beginning, like Deligne's conjecture is about like what happens at the L function when we can actually evaluate it, like at points S, where this is like non-vanishing or does not have a pole order. Remember I said we don't know this L function is actually meromorphic, but let's assume it is meromorphic, like thanks to the Langland's conjectures, which we don't know as well. But let's suppose it's meromorphic. We expect it to be some series with some like finite pole order. And let's assume that like around some values S, it's not a pole order or a zero. We can actually evaluate it. That's what the context of, that's what Deligne is interested in. And, but we need to find out the values of S for which this function, this L function is actually, you can actually evaluate it. So this is where this period morphism comes in. This period morphism, which I will define in a moment, it's defined by Deligne. It tries to cut out a condition where it's so-called critical condition, where this L function makes sense to evaluate. And the story is as follows. I mean, it's a little bit complicated actually. In any case, to begin with, there is a comparison isomorphism between the Betti cohomology and the Durham realization. Like this. And to define the cutting out condition, let's recall the Hodge filtration. So, definition, Hodge filtration. So I have this Durham complex. here X is smooth projective. Starting from the structure sheaf to differentials of first order, then of second order, all the way to the dimension of X. And then I also have the kind of naive filtration. So this is the complex where you have just greater or equal to p degree parts. So this is 0, 0, and then it only starts at omega p. So this the differentials of order p. And in this way, I get like a subspace of the Durand cohomology. So what is Durand cohomology? It's the ith hypercohomology of this complex, of the Durand complex of X. That's by definition, just in case, the Durand cohomology of X. And the naive filtration, there is certainly a map to that full filtration, to the full Durand complex. So I get a map here of omega filtered at X. And I take the image of this map. Okay, that's the Hodge kind of filtration on Durand cohomology. At this case, like, it's not clear what's going on, but one more definition and then we can state the criterion and I give some intuition. So this is the period mapping I infinity plus. So the definition is as follows. It's somehow you can think of it as a real analog of I infinity. So the definition is you start from the Betti realization, and this has some action on the of complex numbers, and you take the invariant by complex conjugation and you tensor that by R, because a priori this is over some Q vector space. Then that embeds into Betti realization of all over the complex numbers, and now I can take I infinity comparison isomorphism and then I project back down to the reals, and then I project again by Hodge filtration. So even though I define the Hodge filtration in this setup only on smooth projective vector space, on smooth projective varieties, it extends in a natural way to pure motives just because they are generated by smooth projective varieties. So of F0 of R. And the definition for, so Deligne's definition, maybe, so the definition like for cutting out the condition of S so that one can evaluate LMS is the following. So we say the This is due to Deligne, by the way. We say M is critical if this analog of the period morphism, I infinity plus, is an isomorphism. So first of all, this I said like we want to evaluate at a random S, and typically there's some integer places, and at least when S is an integer, you can kind of twist this around. So like the motive attached to M, the L function of M evaluated at S is basically the L function of the twist of M of S evaluated at 0. So we can always kind of, at least for integer places, we can kind of twist away the S and just evaluate some motive at 0. And then we say M is critical, kind of this is centered around what happens at around 0 if I infinity plus is an isomorphism. And the intuition for this is that somehow I infinity plus being an isomorphism is connected to the fact that like I define the L function as at the finite places as a product of LP, but there is also like an infinity term, so which I didn't describe, which is somehow like it's a product of gamma functions. And it turns out that like through some playing around, I infinity plus being an isomorphism, so like what happens in the real part, not the complex part, but the real part, is related to the fact that this L infinity term is finite and non-zero. Somehow, some kind of transcendental number going on. And because this L infinity is finite and non-zero, through some kind of, I'm not sure actually, I think functional equation, you can get that at all other places, it's also finite and non-zero. So this is somehow after some playing around that Deligne did, so not easy, obviously. This is the right condition to make sense of being able to evaluate L at M of 0. So in any case, I plus infinity being an isomorphism means that as it's a linear map, that we can let C plus M be the determinant of I infinity plus. So this is an element, a well-defined element in R cross. It's a real number, and up to some rational number, because the choice of this isomorphism, I infinity, also depends on some choice of rational coordinates. So it's well defined in here, and this is somehow called the period of M, if M is critical. And finally, I can state Deligne's conjecture. So if M is critical, then the L function of M evaluated at 0 is equal to this transcendental number, often this period, times some element in the let's say alpha, where alpha is just some rational. Okay, and I guess we can have a look at an example of where this is true. So So for example, let's take M to be the motive, trivial motive twisted by some R, integer R. Then in this case, one can compute. So Lm of 0 is equal to the zeta function evaluated at R. So the L function attached to the trivial motive one can compute is just the zeta function. But twisted by R is zeta function evaluated at R. So this is equal to sum of reciprocals, maybe for R big enough, I guess. And in this case, I mean, of course, like you need to meromorphically continue it for different values of R, right? I mean, for R bigger than 1, it's okay. I mean, this expression here. So in this case, M is critical, and if and only if R is an even positive integer, or R is a negative odd integer. So in this case, Euler, basically like a long time ago, computed that the zeta function at a positive even integer divided by pi to n is a rational number. And this is due to Euler. He proved this using functional equation technique. I mean, at his time, no machine, basically very little machinery was available. But using just some analytical arguments. And in this case, in the negative integer, odd integer, he proved using also functional equation that the zeta function evaluated at -2 and -1 is just a rational number. So in this case, like the period of M is just a rational number, this guy, so it's not transcendental, but here it's transcendental. Okay, it's pretty cool, I guess, that this kind of Deline's conjectures capturing like mathematics from many hundreds of years ago. Let me give another example in the mixed case. So at the moment, everything was kind of in the, for the pure setting. But we can also say something in the mixed setting. So there is also a Deline's conjecture extended. So Anthony Scholl, has extended Deline's conjecture to the mixed setting. Okay. In this case, I just want to give an example of what happens here. So for x, let x be the following curve. So x will be the multiplicative or the punctured disk gm with the points 1 and p in g of m glued together. So this is some kind of nodal curve. And because they're glued together, x is non-singular because it's not flat. Sorry, it's singular. also it's not projective, so it's well away from the pure case. I mean, we can't we don't know the motive attached to X really. I mean, it's meant to be some kind of mixed motive, but using kind of Deline's Hodge 3 paper, we get some kind of mixed Hodge structure on X. So there's some kind of there's some kind of filtration on there. And in any case, due to this mixed Hodge structure happening in low degrees, we expect that these mixed Hodge structures also correspond to some kind of filtration for the conjectural mixed motive attached to X, which we don't know what it is. But we can, if this happens, then we expect this mixed motive to have the following properties. So conjecturally, there should be some mixed motive M of X, and it should sit in a triangle. So you have the pure motives. So this is the Tate motive, because we're dealing with rational coefficients, so like Q, not Z here. M of X and Q. There should be some extension like this, coming from the mixed Hodge structure on more precisely H1 of Betty of X. So if you look at the mixed Hodge structure, which has weights 0 and 1, you get that the conjectural mixed motive should sit in a triangle like this. And moreover, using this Deline's notion of one motives, also these guys were also defined in his Hodge 3 paper at the very end. We can actually compute the L function of M. So it looks like this. So the L function of M of S should be the zeta function of S, the zeta function of S plus 1. So this corresponds to the L function of Q of S, and this corresponds to the L function of Q of 1 of S, times some extra factor, 1 minus P minus S. I mean, the point is, there is no theory of mixed motives, not really, but Deline does capture mixed motives for curves, let's say. So this is X is a curve here, and this is this notion of one motives. So some kind of mixed, if there isn't a big theory of mixed motives, then we kind of already understand what they should be for curves. So the L function, you want through this notion of one motives. And in particular, we can compute explicitly what the L function is, should be. So in this case, L of M at 0 is equal to, through some meromorphic continuation, minus a half log of P. And the M is critical also. And it's determinant of the I infinity isomorphism. is equal to just log of P. So as a result, like in this case, Deline's conjecture holds true because half is rational. Holds in this mixed setting. However, like, I mean, one thing to note is that this motive is an extension of two motives, and the L function of M is not the product of the two outer terms. So it's the product of them plus times some extra factor here. And apparently, like in the theory, which I'm not too familiar with, like this causes a problem when, at least to be able to have some hope in proving this Deline's conjecture in the mixed setting. And so people like look at Deline's conjecture for so-called for a subcategory of mixed motives which satisfy this decomposition property. So like if I have some extension of a motive like this, then in this nice category that maybe Scholl cuts out, then the L function of it will be the product of the L function of the outer terms. So in this category, it's expected that Deline's conjecture holds, and maybe there's some hope to prove, I don't know. But in this setting, like it still holds, but in some kind of the L function is a bit nastier in the sense that I mentioned. But yeah, anyway. Let's now state Deline's conjecture, or try to. Yeah. Okay. So, as I mentioned, Deline's conjecture is concerned with what the L function value is at some finite, finite value, where the values are finite, while Deline's conjecture is concerned with the behavior at poles. But also, it actually also covers Deline's conjecture. So the way it's stated, it covers Deline's critical setting. And also, I mean, it's a generalization of the BSD conjecture for elliptic curves. Maybe this conjecture, the form of it is that I write down is written in 1984. But, I mean, the paper is amazing. Okay. So we need to, it turns out that like a crucial ingredient in Belinson's conjecture is his intuition was that like behavior at poles or zeros of L is somehow related to motivic cohomology. So, and also it's verified in some instances. So in some sense, motivic cohomology is somehow some universal arithmetic invariance, let's say. Okay, the setup is as follows. So we look at a different realization coming from mixed Hodge structures. So I have my category of geometric motives, and now I work over the rationals, so I let k equals q, so this means that I'm looking at varieties over q. I can also look at other things, but let's just fix it for q for now. And of course, my sheaves are also valued in q. And there is a realization coming from Hodge 3 paper in mixed Hodge structures. So now my category will be this category of mixed Hodge structures. So in French, it's mixed structure de Hodge, so the opposite way around, but mixed Hodge structure over R. I think, yeah, I hope you know what a Hodge structure is, but basically, mixed Hodge structure is, so roughly Hodge structure is maybe some kind of decomposition into vector spaces indexed by PQ, which satisfy some dual property, and a mixed one is where there is some filtration, and this is of maybe of weight, pure weight n, where p plus q varies over n, let's say. And in general, some mixed Hodge structure is something like this, where each quotient is a pure Hodge structure. And the point is that the point of Lean's Hodge 3 paper is proving that, like, for X, a variety of finite type, not necessarily smooth projective, that the Betti cohomology of X, maybe of R or Q, some other coefficients, has some mixed Hodge structure decomposition. So in any case, by taking Betti cohomology and looking at its finer mixed Hodge structure, we land in this category. And let's call this functor R. Then, by looking at Hom functors via R, we get the following functor. So, hi of x, so for x in geometric motive QQ, let's say smooth projective, hi of x, well, so I look at motivic cohomology. This is motivic cohomology. Also equal to the Hom of, in this category, of M of x, Q of R, just in case we forgot. And I can tensor this with R, and I land in ith cohomology in this mixed Hodge structure category. So by definition, I'm literally looking at the Hom evaluation. So by definition, this guy here is just equal to the Hom in this category. Of R of M of x of Q of R of Q of R. Well, yeah, R of Q of R, and then tense it with R maybe. So it's literally just a morphism from what you get with the Holmes. And this is called the regulator map. So, it's not quite the case, but let's just call this the regulator map for now. The issue is that one needs to actually descend back down to a billion sheaves somehow, but we can just take this as the definition for now. It's enough complexity for the first go. So then now we have this regulator map. So, which is kind of controlled by motivic cohomology. And now we can state Belinson's conjecture. So somehow what happens at the poles and the zeros is controlled by this regulator map. So so I keep the same x, so x will be some smooth. There is also, so x will be something pure, smooth projective variety, but there is also like several extensions of Belinson's conjecture to mixed settings, finite type setting, but yeah, we won't discuss them. Of Q, and let D be the dimension of X, and M, yeah, I'll introduce them as I go along. So what we're interested in is, so of course there is this, of this motive, of course there is this motive mx, right? And it's expected, like this is, I guess, the Muir conjecture, that this should be a sum of some kind of smaller terms here, a decomposition, maybe D or 2D. So, for example, yeah, and I guess these would correspond to liftings. So these pieces here, they look like X and some projected, maybe P1 here. There's maybe some twist, but the point is these P1s, we don't know that they exist, right? They map to pi1 under the Kunet conjecture. And Belinson's conjecture is interested in describing not the whole of M of X at one go, but the finer pieces HI. So he wants to describe the L function behavior at these HI of X. So for example, as an example, we know that the motive of an elliptic curve, it splits as trivial motive plus this piece H1 of E plus Tate module. And for example, the L function of H1 of E of S, we can, I defined it like formally, but in literature, this is also the same as the Hasselbalch zeta function. So So there's a kind of down-to-earth definition of like the definition of the L function for a general motive that I wrote down is a bit abstract, but it certainly works. But there is a down-to-earth definition of like, in terms of number of points modulo p at the special fiber, and so on. And this is something called like the Hasselbalch zeta function of a variety, or of an elliptic curve maybe. And this corresponds precisely to the definition that I wrote down before for the L function of a motive, of this H1E motive. So it's natural, for Beilinson setup, it's natural to investigate what happens at the L function of these pieces, not of all of Mx. Of all of Mx, it will just be a product of the L functions of these pieces. So he's interested in the L function of, let's call it HB minus 1. I just write B minus 1 for convenience here, but it can be an index of X of S. So again, like, we don't know in general whether this HB minus 1x in this decomposition actually even exists. For elliptic curve, certainly exists, but in general, like, it's the content of Muir's conjecture that the Kunet, well, not strictly speaking, you don't need all of Muir conjecture. Muir conjecture says that the motive splits completely in terms of these pieces, but all you need is the Kunet conjecture, that the cohomology classes pi I lift to algebraic classes, and this gives rise to these HI pieces. So in general, we don't know that this thing exists, but suppose it does exist, then the order of a pole or a zero of this L function is equal to 0 if B, so here is B here, let me write it clearly. B minus 2m is less than or equal to minus 2. It's equal to minus the dimension of the rational Chow ring of codimension m, quotient out by the Chow ring up to homology equivalence. If B minus 2m is equal to minus 1. The reason why you have so many cases is like the L function, due to the L function, due to the functional equation. So this is case 1 maybe, case 2, and case 3. It's equal to the dimension of just the homological equivalence class of X if B minus 2m is equal to 0. And the fourth case is it's equal to the dimension of the motivic cohomology itself of X Q B minus m if B minus 2m is greater or equal to 1. Okay, that's the first part of Beilinson conjecture. I mean, Beilinson conjecture, he wants to predict the order of the poles. So this number here, it's equal to, I mean, if you start, for example, at some number at s minus m to the power of n plus some number at s minus m to the power of n minus 1 plus so on plus, some number plus some number s minus m and so on. This number here by definition, this is the L function, sorry. This number here is equal to n, capital N. We're interested in the pole order, basically. Or it could be a zero order. And the second part of Bellingsen's conjecture, so that's the first part. Is what is this number here? So an, like, what is this, the leading term? And the situation is as follows. So one, like, again, there's many cases. If b minus 2m is greater than 1, then it is conjectured so here, like, there will be conjectures within conjectures. It is conjectured that the regulator map R infinity of hi x q b minus m tensor with R to hi of the mixed Hodge structure of x R b minus m. It's conjectured that this map R infinity is an isomorphism. And so let d infinity be its determinant. Here there is no choice ambiguity. And then the conjecture is basically that this leading term, an, then the conjecture is that an is equal to d infinity modulo some rational unit. So it's completely, the leading term is completely governed by the determinant of the regulator in this setting. B minus 2m is greater than 1. Let's look at in the other settings. So in the setting, b minus 2m is equal to 1. So this is also the point of symmetry of functional equation. Of L. Just in case, the L function, it's conjectured to satisfy some functional equation. And it's, there are two terms on left side, right hand side, and by swapping the terms, there's a point of symmetry, and this is the case where it happens. So in this case, it is conjectured that this map, so it's a big map. So on the one hand, I have the rational Chow group, quotiented out by cohomological equivalence. And then I sum that with h of 2m plus 1, the motivic cohomology. So clearly there's something deep going on in these conjectures, right? There's some control of these leading terms in pole order. governed by motivic cohomology. So this tensor with R, so there's a map like this from here to the cohomology of this mixed Hodge structure thing. And it's conjectured that this is an isomorphism. So just in case, like this second map, the map from here to here, this is the regulator map. And this map here, let's call it F. I will write down what F is here. The map. So F is given by the composition Another thing to note is that to state Berlinson's and Deline's conjecture, we didn't really need to do mixed motive theory, right? I could have, I guess, stated it fairly early on in the lectures. So this map here is, first you compose with the class map to de Rham cohomology. And then there is some spectral sequence called the de Rham spectral sequence, Hodge to de Rham maybe, Hodge to de Rham spectral sequence, which when you analyze it, there is a term that there's a map that goes from the 2mth degree to the 2mth plus 1th degree. Of this guy. Okay, so in any case, this map is conjectured to be an isomorphism. We let d infinity be the determinant of the previous map. Then the conjecture is that the this AM term is again equal to this d infinity modulo some rational unit. And finally, the last case, what happens at b equals 2m. I mean, I consider the cases b minus 2m is greater than 1. This was the case where b minus 2m equals 1. And now I'm considering b equals 2m. And you can get the remainder of the cases by looking at the functional equation, the symmetry of the functional equation. So in any case, at b equals 2m, there is something different going on. So like no motivic cohomology appears a priori. What happens is the following. So in some paper of Berlinson, so in a 1987 paper of height pairings, Berlinson constructed some pairing. So from the Chow group of codimension M up to homological equivalence of X with rational coefficients times the Chow group of D plus 1 minus M. Recall D was the dimension of X into R. So this height pairing, it's not, if I just take naive intersection, like if I take an intersection of something of codimension M with codimension D plus 1 minus M, I get codimension minus 1. So it doesn't make any sense. So naive intersection here doesn't work. Not naive geometric intersection. So Beilinson, this height pairing is some kind of arithmetic intersection. So it's an arithmetic, without saying anything more. It's conjectured, again this is like a conjecture within a conjecture, but it is conjectured that this height pairing is perfect. So let H infinity be its determinant. And then the conjecture is that this AN leading term is equal to H infinity times the transcendental period of this HB minus 1 of X. So I guess for this motive, this motive is expected to be critical, I guess, in this case. Otherwise, C plus doesn't make any sense. And modulo rational units. Okay. That's the end of the second part of Beilinsen's conjecture. As you can see, it's quite big. I mean, to state, at least. And there's obviously a lot of deep things going on. I mean, clearly something like an L function. I guess the motivation to even write down an L function is, it's simple. Like, you just want to study points of the number of points of some variety, right? Like you have some variety and you just want to ask, like, how many FQ points does it have? This leads, like, this is an arithmetic question, but it's kind of hard to study. Like Diophantine equations is hard to study. So the idea is, let's use analysis to study it. So an L function, let's write down a generating function for these values that I want to know. I want to know the number of points, FQ points, the number of FQ squared points, and so on. So let's write down a generating function in the hope that I can use analysis. And what is that generating function? It's exactly an L function. So now, like, the study of an L function is very natural. And it turns out that, like, so starting from these elementary questions, it's conjectured that these L functions capture some very serious invariance of my starting variety. I mean, in some case it captures some height pairing. In other cases it captures motivic cohomology with some mixed Hodge structure. I mean, it's like kind of crazy, actually. So Beilinsen's conjectures, there are even, I mean, what I stated here is for pure motives. I mean, there's extension to mixed motive as well. There's refinements, etc., by work of Fontaine-Perrineau, Locatto, and